Okay, guys, so introduction to neural networks. However, before we start, I would like to clear out one thing that we are probably not going to able to finish this presentation in time. So we might be doing it again next week because I have over 90 slides, okay? So neural networks are no easy thing. So we have a lot to cover, okay? So we move forward. How do I move forward? Okay. Why it is not moving forward? Okay. So agenda, you would know it if you sit through the presentation. Okay. So yes, sit tight and enjoy. Okay. So first let me discuss. Okay. First, let's talk about what neural networks actually do. Okay, we want to understand what a neural network is actually doing. Once we understand what it is actually doing, it's much easy for us to move forward and understand different aspects of training and testing and all that. Okay, so let's imagine you have a university application data set. Okay, so you have the grades of the students and the test scores of the students. So grades is the grade they obtain in school, and test that the score that they got in the entrance test for the university. And I say, okay, this is how the data set looks like. Okay, so you have these blue dots and the red dots. The blue dots indicate the student got selected. Okay, they got accepted into the university, and the red dot indicate that the student got rejected. Okay, now just looking at this data set, okay, this distribution scatter plot, yeah, to be more technical. If I ask you, can you draw a line that separates this data set into two parts such that on one side you have students that got selected, and on the other side you have got students which got rejected. Okay, so just by looking at it, you'll probably think, okay, I might draw a line like this. Okay, so yeah, this is probably what you're going to do. Draw a line like this, and there are some students which are on the wrong side of the line, but okay, let's just ignore them for the time being. Okay, so we do this, and now if I say you draw this line, okay, you drew this line, very good. Now can you find the equation of this line? Okay, the line that we have drawn has an equation of the form y is equal to mx plus c, okay, or you might want to call it y is equal to mx plus b. Okay, where b or c is the intercept. Okay, we call b as the bias. So if I reformulate this equation of line and try to put it in a neural network C way, okay, there is a neural networks have their own language of sorts. So let's put it in a way that the neural network can understand. So on the input, you're getting an input data, okay? So on the y-axis, you have student grades, and on the x-axis, you have student test scores. So you're getting 2 points for every student. Every student, you have grades and the test scores. Now reimagine it, just reimagine this and say grades are x2 and student test scores are x1. Okay, simple. Nothing complicated over here. We just call it x1 and x2. Don't get confused with this y-axis and x-axis. I'm not talking about axis. There's just x1 and x2. So now if I say what is the equation of this line, you can actually say 2x1 plus x2 minus 18 equal to 0. Okay, if I put everything on one side of the equality, this is probably what the equation is going to look like, which is basically saying x1 is your test, so 2 times test plus grades minus 18 is equal to 0. Okay, so this equation, this becomes your score. So if I give you the grades and test of a test score of a student, you put that in this equation, okay, and what you'll obtain is a score. If that score is more than 0, okay, that is the point is on the right side, then that means the student got accepted. If if that score is less than 0, that means the student got rejected. Simple. Okay. So can you guys see my mouse pointer, by the way? So just write yes in the chat.
Yes, it's
Yeah,
visible.
perfect. Yeah, that's perfect. Okay. So that's what our system does right now. Okay. We have drawn a line. If a student falls on the other side, we say accepted. On the other side, opposite side got rejected, and we have defined an equation for this line in a way that is more neural network friendly. Okay, this is just an equation of line, nothing fancy. So what I do is, oops, yeah. What I do next is I can put this in a more general form, right? The mathematicians want to put everything in a more generic form. So instead of this 2x1 plus x2 minus 18, I put it as w1x1 plus w2x2. Notice w1 and w2. Okay, the coefficients of x1 and x2, which is 2 and 1, these are our weights. We call them as weights, w1 and w2. These coefficients are supremely important. Okay, I mean, everything depends on them, and we're going to know that, in a while. Okay, so W1 and W2, W1x1 plus W2x2 plus B is equal to 0. This is the form of this line, and we can just put it in a linear equation form, which is Wx plus B is equal to 0. Okay, so always remember, when you see this, just go back in your mind and remember that all this is coming from this form of equation, and this equation is coming from this equation of line. Okay, so it's just an equation of line at the end of the day. Okay, so don't get confused. So we have, our prediction stays the same. As soon as we give in a test and a grade, what we produce from Wx plus B is, whether it's 1 or 0, it becomes y cap. Okay, if it is Wx plus B is greater than 0, it becomes 1. If it is less than 0, it becomes 0. Okay, that becomes a prediction. And what we have already, okay, this data set that we have already, these dots, whether they are falling on this side or that side, they are known as labels. Okay, this is the label 0, and this is label 1. Okay, it's simple. By the way, this line is also known as a decision boundary. Okay, in more fancy terms, this is called as a decision boundary. Now what I need you to think is, you had a 2-dimensional data set. Okay, we had this 2-dimensional data set, and I asked you to separate in 2 parts, so that on one side you have students who got accepted, on the other side you got students who got rejected. You drew a 1-dimensional line. Line is 1-dimensional, so you draw a line. Okay, that line is 1-dimensional. You had a 2-dimensional data set. You drew a 1-dimensional line. What if you had a 3-dimensional data set? Okay, so instead of just grades in tests, let's say I add another axis that's, I call it rank. Okay, that becomes a 3-axis, three-dimensional data set. What you're going to do then? You're probably going to draw a plane. Okay, so always remember this. It's going to come in, pretty fast. So if you have a 3-dimensional data set, you're going to draw a 2-dimensional plane to separate this data set. Similarly, if you have an n-dimensional data set, what you're going to do, you're going to draw an n-1 hyperplane boundary. Okay, this is not something that you can imagine. It is a mathematically abstract. This is abstract maths. This is pure maths. This is a mathematical concept. Okay, it's just something to get an intuition of. So this is how this whole thing is working. What actually our system over here, which is just started from equation of line, what is actually doing is just drawing a boundary. Okay, and that boundary could be in 2 dimensions, 3 dimensions, or n number of dimensions. Okay, and that's what we're doing. So now we move forward. What if we had more data? We had x1 to xn, so many different parameters on the students. We are going to draw an n-1 dimensional hyperplane. Simple. That's what I'm talking about. Okay. However, there is something interesting you should know. There's some terminology. These columns, okay, these different points, data points on each student, x1, x2, I call it x1, x2, x3. Okay, the exam 1, exam 2 grades. These are the actual numbers, but in terms of mass, if I call them x1 all the way to xn, these are features. Okay, these are the features. And the output, as in whether the student got selected or rejected, it's called y. This is your target variable. Okay, this is what you're trying to predict. So output is like, okay, if you say you talk like, okay, this student got 9, 6, and 5 in exam 1, 2, and grades, let's say 6. Okay, in network is saying 1. Okay, he got accepted. This one is saying, okay, got rejected. So these x1 and x2 are called features, not in neural network lingo, but this is just general machine learning lingo. Okay, and your y is the target, which is what we are trying to predict. Okay, so if I say, okay, these equations are fine, but let's add some graphic design to this. Okay, so we are going to add some graphic design to this. Let's make them look super cool. How you can make them look super cool is you can actually have these nodes which are called as input nodes. Okay, it's the same equation. Okay, it's the same thing. Input nodes, test, grades, and bias. And then everything is getting summed up in this one node, okay, and which is basically just calculating 2x1 plus x2 minus 18. So 2x1 is your test, yeah. So x1 is my test, so that's 2 cross 7 plus 1 cross 6, which is grades, and minus 18 into 1, which is a bias, equal to 2. Now notice that if this is greater than or equal to 0, which was this, your output is 1. Okay, this we say that, okay, neural network got activated. Okay, it got activated and it gave out an output 1 for these inputs. If the score was less than 0, it will give out an output 0. It didn't get activated. So this inequality, notice this. We call this inequality over here. It's an activation function. And it's getting activated if your input is greater than 0. Okay, and over here we have a simple step activation function. So I just generalize this, what we have been talking so far. So you remember this equation wx1 plus wx2 plus b. You can actually take it all the way to wn xn. Okay, this is this. So this looks like this. It's an input vector. If I dare say, call it input vector x1, x2, xn. Okay, this is your input. These are your weights, and this node is actually calculating just wx plus b, just the linear combination, okay, of these inputs multiplied by weights. Remember this term, linear combination. It's happening everywhere in your networks. Okay? So there's this linear combination of this, and then this gets pumped into a step function, which is basically calculating this. Okay, so in previous diagram and this, there is no difference. It's just that over here the step function was inside the node. Over here it's outside, just to make it look, just to show you what is actually happening inside. Okay, so let's generalize it even more. If you generalize it even more, this is how it's going to look. So wx1 all the way to wnxn. This is a linear function. Activation is by a step function. So by the way, a step function is the activation function, and there are a lot of different activation functions, including an activation function called MISH, which was actually created by one of our peers, which is so cool. So we have these different kind of activation functions. Over here we are using step function to just keep everything simple. Okay. By the way, what you see over here is something that we call as, there's a name to this thing. Okay, it's called something, and it's called a perceptron. Okay, so this is how, my friends, I met the perceptron. It's for all those who didn't get the reference. Okay, so what we want to do actually is that we want our perceptron to figure out this line all by itself. Okay, over here we told, okay, we told the perceptron, okay, this is the equation, this is the line, but that's the equation 2x1 plus x2, blah, blah, blah. But actually what we want is, we want the perceptron to figure this out by itself, okay? And that is where all the hype about machine learning comes into, okay? Mechanism to find line automatically, mechanism to find this line automatically, learn the value of weights, learn, that's, that's interesting, learn the value of weights, W1 and W2, and eventually machine, want the machine to do machine learning. That's what all the hype is about, okay? At the end of the day, at the very bottom, poor thing is only drawing a line, okay? And we're going to see that. So what we want to do is, we want to figure out these weights, W1 and W2, so that we get this line of best fit, or which best separates our data. Okay, it could be either ways, whether it is a classification or regression problem. Okay, so that is what we want to do. So how do we do this? Okay, so now we are going to get into a little bit more maths, and the way to do it is, let's imagine a single misclassified point. Okay, let's imagine a single misclassified point. And this is, let's say, this is your decision boundary. Okay, this is the line that you drew. Now my question is, what do you think should happen if you want to perfectly classify this point? Whether you want this line or decision boundary to go away from it or to go towards it. Think about it. What you want to actually do is, this line should come towards the line, towards the point, okay? This line should be coming towards the point, so that this point becomes properly classified, because this is a red point, should be in the red zone. So yeah, so the decision boundary go farther or come closer to it, it should come closer to it. Okay, so let's put some numbers to these, to this boundary, and let's do some math, simple math. Let's say the equation of this line was 3x1 plus 4x2 minus 10, some equation, okay? And the point says come closer. It's a red point on the blue side. So if you want this boundary to move closer to this point, what you need to do is, you have these are the coordinates of the point. You just subtract those coordinates from the weights of this line, okay? These coefficients 3 and 4 and minus 10, you just subtract the weights from this. Subtract the points of the subtract the coordinates of the point from this. Okay, so you subtract, you'll get some number. However, there's a catch to this. What happens if you actually subtract, the coordinates of the point from your equation of line, from your weights directly? What happens? The whole thing will just change too quickly. Your decision boundary will just jump around. And what would happen in the process? It's going to misclassify a lot of properly classified points. Okay, you don't want that. So what you do is, you actually introduce a factor. Okay, and we call this factor as learning weight. You introduce a factor called learning weight, so that the line moves, but it moves slowly. Okay, it's obviously a number which is less than 1. Well, no, not really. It could be any number. Sorry, it doesn't have to be less than 1. But however, mostly it is less than 1. Okay, it's a fractional number, so that the line that you're moving, the decision boundary that you're moving around, is actually doesn't moving so fast. Okay, if it moves too fast, it's just going to go crazy. So you multiply your points, the coordinates of this point, by learning weight. So you do this multiplication, and then you get the new line, which moves slowly, just a little bit towards your point, not all the way. So with this, we come to something called as the perceptron algorithm. What is perceptron algorithm? We agree to this fact that if we subtract this, the coordinates of this point, the line moves towards this side. Similarly, if the point was on the other side, instead of subtracting, we'll basically add. Okay, it's just the reverse thing that happens. If we do this and we keep on doing this, we eventually are going to properly classify most of the points, not all the points, okay? Not all the points, most of the points. So this is what we call as a perceptron algorithm. What we do is, you start with a random weight, okay? You start with random so these coefficients of these, x1 and x2, you just start with a random number, okay? Start out randomly. And then you look at all the points that were misclassified, okay? For every misclassified point, what you do is, if the prediction is equal to 0, okay, that means you have a blue point, a blue dot in the red area, okay? What you do is, you basically just, you see if the prediction is 0, it's just misclassified, the blue dot is misclassified. What you do is, you do this, okay? You take the coordinates of the point, multiply this by the alpha, which is your learning rate, and you update the weights, okay? So what we're doing is, we are updating these weights. This line, okay, this equation of this line, this W1, W2 just got updated like this, and this is the bias. It's got also updated. This is exactly what we're doing. We are taking these the coordinates of the point. This xi is, this is the coordinate of that point, which is misclassified, and we multiply that by alpha, which is your learning weight, and then you change the weight, okay? And then you also change the bias, which is d plus alpha, which is your learning weight. You do similar thing for the point which is on the other side, okay? Instead of adding, you do a subtraction, and that is it. You run this algorithm for maybe a set number of iterations, maybe 5,000, 100, 10,000, could be anyone, okay? Or till you find a good enough accuracy on your predictions, okay? So with this, what you can say is, you have a data set and you have a perceptron. If you have a data set and a perceptron, you got the line, okay? Data set, perceptron, line, data set. For all those who didn't get the reference, okay? So now the catch is, there's a catch. The catch is that seldom our data is linearly separable. Linearly separable by meaning, like, you cannot really draw a line and have two sides of it. It really isn't like that. What you actually have is something like this. You have a data which cannot be linearly separated. You cannot draw a line like this. You probably need some kind of a curve, okay? And that's where your perceptron, single perceptron fails. However, what if we combine multiple perceptrons? Virus in numeris, power of numbers. Okay? If we combine multiple perceptrons and see how this goes. So this is like a real deal intuition behind what neural networks actually do. So what we do is, we take a perceptron where your decision boundary is like, it's like this, and then another perceptron where decision boundary is, it's like a vertical decision boundary, and you combine this. And when you combine this, you will get a combined system whose decision boundary is somewhat what you're looking at, okay? So if I just I'm just putting numbers, okay? These are just numbers. Okay? So if you put like 7 to this and 5 to this, probably because you want more curve over here, so you give more weightage. This is the weight. You give more weightage over here and less weightage over here. So what you do is, you combine this and you get a curve boundary. Okay, so simple perceptron combination. So let's say I combine 2 perceptrons. Okay, let's put more numbers. Take 2 perceptrons and I combine them with a third perceptron. Okay, this is one perceptron, this is one perceptron, and I combine them. Always remember, at the end of the day, what the perceptron is doing. It's just drawing a straight line. Okay, it's just drawing a decision boundary, not straight line. It's drawing a decision boundary. Okay, So we take these perceptrons, we combine them, and what you get is, boom, you get a non-linear decision boundary, which is absolutely insane. This is amazing if you think about it. Okay, let me just, so by the way, this diagram and this diagram are same. Okay, there's no difference. It's just, this is more, this is a better way to represent it. That's how we draw neural networks. What we are doing, we are combining two perceptrons with a third perceptron, and the output that we are getting is a non-linear boundary, which is, wow, which is absolutely amazing. Okay, and what if I add another layer of perceptrons in the middle? Okay, so what we did over here was, I had this layer and then I just had an output. What if I add more perceptrons in between and then I have an output? Boom, that's what deep neural network is. You get a non-linear hyperplane. Okay, so this is just a 2D representation. What you're going to get in reality is a hyperplane which is absolutely non-linear, and that is why neural networks are the most powerful machine learning technique out there. That is why you have so much accuracy with neural network techniques, okay, with neural network algorithms, because neural networks know how to draw non-linear boundaries. Okay, so yeah, this is where perceptrons go super saiyan. Okay, this is the power of the perceptron. When you combine them, you get a deep neural network, and boom, this is the Kamehameha moment, people. This is the Kamehameha moment for perceptrons. Okay, so now what you know, what the neural network is actually doing. Okay, people say AI is going to take over the world. The poor thing is only finding lines that best fit and classify the data. So, well, before we move forward, Helena, we can take a few questions.
Yes, Pranjal, I have one question from Sam, and that is, what if my data set weights have almost the same value?
Okay, so if your data set weights, well, by the way, you do not have weights in the data set. So maybe he wants to know what if your weights have the same value as in that equation, that boundary line equation that we drew, if it has the same weights. In that case, if you have the same weights, you're going to have problems with backpropagation. Okay, if the weights are the same, it creates problem with backpropagation, and when you're backpropagating, it could happen that your weight doesn't change over multiple iterations, and that creates a problem. So it's always better to, in a deep neural network, to initialize your weights in a form of a random normal distribution, okay, as a normal distribution. That basically helps in converging your neural network. So I hope that answered his question.
Thank you, Pranjal. And we have no other questions so far. If you have a question, just write them in the chat and Pranjal will answer them.
Okay. I think we're going good. Yeah. Okay. So we move forward. So yeah, here's a meme for everyone. Is this a Skynet? Well, no, it's just, well, it's just drawing decision boundaries. It's not a Skynet. How do I move forward? Okay. So now we have understood how neural networks actually work and what a neural network is doing. What we want to do is, get into more maths. So training and evaluating deep neural networks, okay, it's not that straightforward. So we have to dive into maths. By the way, this is for maths theorem. Okay, so the question is how we numerically calculate the deep neural network output. Okay, how do you actually calculate the output? You have some. So my question is simple. Okay, you have this. Where is that equation? Yeah. Yeah. So you have a combination of perceptrons, and you want to know a y cap, y hat. Okay, and it's not this simple. You have this whole multiple layers of maybe hundreds or thousands of layers of these neurons or perceptrons. Let me call them neurons now. And you want to calculate y hat. So how are you going to do that? So it's not that straightforward. So let's do that. Okay. So the way to do that, way to calculate that is feed forward. Okay. So let's first try and ponder what our neural networks actually contain. Okay. What they actually contain at the end of the day. You have a set of weights. First, you have these input nodes. Okay, you have this input, you have these input nodes. Then you have this set of weights. And then your network is basically doing a linear combination, and through an activation function, there's some output. Okay, and there could be hundreds or thousands of these nodes. That's what your neural network actually has. And there can be multiple layers, so there can be more weights, not just one side of weights. There can be more set of weights. So this is a more accurate representation. You have an input layer, you have a hidden layer, you have two hidden layers, multiple hidden layers, and then you have an output layer. So in the output, you can have a single output or multiple outputs, depending upon if you have a multi-class classification. Okay? Could be anything. So if you look at this, what we find is you have inputs, which is this. You have weights. Weights, you have three different kinds of weights now. Now it's just not one weight now. You have a whole weight matrix going on. Okay. You have input to hidden, so input to hidden weights. Then hidden layer 1 to hidden layer 2 weights. There's a weight over here. Okay. All these lines have basically weights associated with them. Then there's these weights, and then from this hidden layer 2 to the output, this also has some weights. Okay, so now we have a whole complicated bunch of matrices moving around. It's not just a single number going back and forth. And then you have these hidden layers, of course, and then output, which is just one input. Okay. So if now I want to describe a neural network as in a form of a black box, what I'm going to do is I have these, listen carefully. We have these n inputs. These n inputs are from x1 all the way to xn. Okay, so now this becomes a vector. Now this is a vector. This is not a single number anymore, guys. Okay, so it's called x bar. It's x underscore bar I've written because I couldn't write x bar. Okay, so now it's x bar, n number of inputs. Then you have a black box neural network, which gives you k number of outputs. Okay, and it's like a multi-class classification. It could k can be 1 or k can be 1,000. It could be anything. So what is actually happening? Your k outputs are now also from y1 all the way to yk. So it becomes a y bar. And then you have these weights, which is there are some weights inside. It becomes a matrix. Now we have a weight matrix. So neural network is what actually is doing, as we saw before. It is just calculating a nonlinear boundary. So it is acting like a nonlinear function approximator. So this is how universal nonlinear function approximator. You can describe that in this form. So you have y bar, which is your output. And then you have this nonlinear function, which is your neural network is doing something inside. And then you have x bar, which is your input. You get these y bar based on x bar and some weights. That is what is happening. So if we move forward, what actually our neural network is now doing is you have this non-linear boundary, okay? And as soon as you get an input x dash, it is supposed to predict an output y dash. By the way, this is a regression example. Okay, so far we had been seeing a classification example where you had a decision boundary and your neural network was trying to classify whether the point should fall on the upper side or the lower side. Over here, this is a regression example. Okay, so you have this data set and you give it a new point x dash, your neural network is trying to predict y dash, and you ideally would want it to be somewhere around this. That's what your neural network is doing. So there are two kinds of problems that neural networks can solve. I mean, as far as I understand, there are only two kinds of problems. Correct me if I'm wrong. Okay? Tell me in the chat if I'm wrong. There are only two kinds of problems that a neural network can solve. One is classification, and the other is regression. Okay? There's no third problem. Every other problem can be distilled into some form of combination of regression and classification. Okay? So classification is simple. We know what is it. Regression is, you get a continuous data like your stocks, the price of your stocks, and you get the output, what's the price going to be tomorrow. This is, by the way, my favorite application. This is what I'm working on. Okay. So how a generic deep neural network is going to look like. You have these input vectors, x1 to xn, mark my words, vectors. Okay. Then you have this weight matrix going from x, as in going from input to the hidden layer. I call it W1. And then I have, then these hidden layers outputs are going from hidden layer to the outputs through this weight matrix called W2. Okay. So I have this hidden layer neurons from H1 to HM, and then the output from Y1 to YK. Okay, this is a generic neural network. So you might question, like, what is a weight matrix? And this is very important to understand. How a weight matrix is actually laid out. Okay, this is an important thing to understand. Because when you're coding neural networks in pure NumPy without using any libraries, you need to understand how the weight matrix is moving around. So this is a very good illustration of a weight matrix is. So for W1, this is specific for W1. All the weights which are leaving the input nodes are aligned as rows. Okay, and all the hidden units where these weights are ending are aligned as columns. Let me say it again. All the input nodes from where these weights are originating, okay, they are aligned as rows, and the points in the, not the points, and the hidden layer where these weights are finally ending is aligned as columns. Okay, so these are hidden layer neurons, not hidden layer, but hidden layer neurons. So this is your input vector. Okay, this is your input vector. This is your hidden node vector. This weight matrix is aligned like this. Okay, so if you look at the other image, the one on the extreme left, you have x1, x2, x3. Okay, so weights W1, W21, W31 leave from x1, x2, x3, but go only to h1. Okay? And similarly for the other node. So if you want to put it in a matrix format, this is how you're going to put it. So input units, rows / rows, you call it rows or units, whatever. Not input units, because you can have a deep neural network, you can have multiple hidden layers, so you cannot call it input unit as such. So on your rows, you have weights originating from layer HP. Let's say we have P number of hidden layers. This is like H1, this is H2, H3, all the way to HP. So as rows, you're going to organize weights originating from layer HP, and then the columns of those matrix, weight matrix, are going to have the number of nodes in the layer HP plus 1. Okay, so give yourself a little time, go, think about it. It's a little abstract concept, how this matrix is actually constructed. Okay, so we move forward, and now let's say we want to do a simple feed forward. Okay, so first you need to understand what is a feed forward. Now, remember, we wanted to figure out the output y hat of our neural network, of a deep neural network. To get the output y hat of a deep neural network, you need to perform a feed forward step. Okay, you basically need to perform a feed forward. What is a feed forward? You push your inputs from the left side all the way to the output. It's like the Super Saiyan, Kamehameha. Okay, so what you need to do is first we see how we're going to calculate the input layer. Okay, not input layer. How we are going to calculate the hidden layer. Okay, hidden layer Hi is a nonlinear function of input weights Xi multiplied by, or basically modified by, the weight matrix W1. Okay, so your hidden layer is a function of inputs modified by weight matrix W1, all encapsulated in a nonlinear function, activation function. Okay, this is what that crazy looking equation is saying. There's too many subscripts and superscripts. That is what it's saying. That is how you create Hi, the hidden layer. And now, how your output Yi is going to look. Yi is nothing but a function of hidden layer activations, which are Hi, which we just calculated in the previous step, multiplied by weight matrix W2, and then passing through an activation function, nonlinear activation function F. This is how you do a feed forward. This is like a 20,000 feet view of feed forward. We will go into depth. We'll try and calculate exactly what is happening. Okay, so how each neuron is looking like in this case. The way each neuron is looking like is this. Okay, you have a summing function, and which is basically calculating Wx plus B. Okay, don't forget that. And you have these inputs all the way to x1 to xn. You have these weights. You have the bias. This is where Wx plus B is being calculated, all in a vector format now. Now we do not have just one W1 and X1, guys. We have this whole vector. Okay, and that is why Python is one of the best languages to learn machine learning, because it is inherently vectorized. Not Python, but NumPy. Yeah. Okay, and then everything is being squished through an activation function, which is denoted by phi, and here you get the hidden layer activation. So on the left hand side, I've deliberately kept that perceptron image that we saw some time back. This is exactly what is happening over here, guys. Okay, it's just a perceptron. Each neuron is just acting like a perceptron. It is a perceptron. So now let's calculate a feed forward. Let's do the maths. Let's get into the maths now. So you have your input vector x1 to xn, which is called as x, and then you have your weight matrix W1, and then you have your hidden layer H1 to H3. Okay, to just keep everything simple, we just have 3 neurons in the hidden layer H1, H2, H3. Okay? Otherwise, it just becomes a little complicated. Step 1, we need to find H. Okay. Step 2, we need to find the y bar or y cap, y hat. It's not y hat anymore, it's y bar because you have a vector. Okay. Then you want to find y bar by matrix multiplications. So let's go forward with this. Let's move very slowly. you have these input vectors. In the middle, you have weights, and in the output, just for ease of understanding, let's just call this output at the moment. You have the output H1, H2, and H3. So you have given X, find H. X bar, find H bar. So first, this is how the weights are laid out. And this is for the memory aid. This is how the weights are going to be laid out, okay? This is your input units, W1, W11, W12, W13. And this is your output, which is H1, H2, H3. So this should have actually 3 columns. It has only 2 columns. It should have 3 columns because all these weights are originating from X1 all the way to Xn, but they are ending in only 3 different nodes in the hidden layer. So they should have another column over here. But this is just for, just for you to remember. So this is our situation. What we have is we have a vector, we have a row vector. Okay, we can put this as a column vector as well, by the way. X bar is represented as a row vector. We can put this as a column vector as well, but then our this matrix multiplication and all that, it just goes, it just becomes too complicated. So that's why we have these row vectors. And NumPy also helps you in taking, doing matrix multiplication when you have this as a row vector. np.dot function helps you in this. So that's why we keep this as a row vector. So you have a row vector X bar, X1 to Xn. You have this weight matrix. This is a proper representation of weight matrix. W1, which is, which we just saw how we are going to lay it out. And then you have the H dash, which is H dash 1, H dash 2, H dash 3. By the way, this is not H1, H2, H3. Okay, these are not the final outputs. This is the intermediate output. Okay, we will see further how we're going to calculate this. So a simple feed forward from the inputs to the hidden layer is going to be like this. You have these vectors, a row vector, and you should immediately connect this with how you're going to get your data in your Python. Okay, as a NumPy, NumPy vector, you need to get this as rows. And if it is not in rows, you have to reshape it to make it look like row. Okay, it's important. And then you have your weights where you have n rows and 3 columns. Why we have n rows and 3 columns? Because of this. Okay. And to calculate H1 dash, H2 dash, and H3 dash, you just do a simple dot product. It is as simple as a dot product, which is also, I think, Hadamard multiplication, but okay, let's not get into that. Anyway, so this is H dash 1, X1 dot W11, X2 dot W21, which is basically a simple multiplication. You draw a simple way to figure out what's going on is you draw a line like this and you draw a line like this. So this and this are getting multiplied element wise, and then everything is getting summed. Okay, that's a way to remember it. So now you see we are doing H dash. This is still not H, so we need to apply an activation function. So we talked about activation functions. They can be, initially we saw a step function which was just giving 0 or 1. If you give value greater than or equal to 0, it's going to be 1, else it's going to be 0. Otherwise, you have these hyperbolic tangent functions, sigmoid function, which just squishes everything from 0 to 1, and then value function. So by the way, activation functions do a lot more than just squishing the output. They actually convert your discrete output of the neural network into continuous probability space, but I'm not going to get into that because we already are running short of time. Okay. So that would unnecessarily we have to branch out from this and do a lot of probability based calculations. But that's what is actually doing apart from squishing. Okay. So it's not just the squishing thing that it does a lot more. So we calculated H dash, and now H bar, the whole this, if you want to push it through the activation function, we call activation function as 5. That's what we do. You do the H bar is actually dependent on the inputs X bar, which is your input, with a dot product W1, which is your matrix, which was a matrix between X inputs and H hidden layers, okay, squished through an activation function. That's what your H is. Okay? That's how you find H. So each individual H is going to look like this. I'm not going to read it, but that's how it's going to look like. Okay. Okay. So now we have calculated H. We got our H. Now we need to calculate Y. Pretty simple, guys. Now you know how. Now you know the drill. You have the weight W2. You have H1, H2, H3. You just need to do a matrix dot multiplication, right? Matrix dot product. So you have W2, which is laid out like this. Okay. So again, look at this. How many rows? The number of weights that you are, that are originating from here, and then number of columns, the number of outputs. Number of columns, number of outputs. Okay. So now we want to calculate Y, which is simple multiplication dot product of H1, H2, H3, and W1. All this. Y cap or Y bar may or may not be passed through an activation function. Okay, that depends what you want to do with your neural network. So this is how a simple feed forward looks like. You see, these are the equations. So once we have the output, okay, yeah, Helena, do we have any questions?
Yes, we have one question, and that is when you had that weight with rows and columns, and we had a question if both are columns.
Sorry, can you say that?
So the question was both are columns, right, in the chat. So when you had that box with the weights and you talked about the columns and the rows, there's a question if both are columns.
Hi, both are columns, right? That's Akash is asking.
Yes, that's correct.
Both are columns. At what point did he ask that question?
This was when you introduced the weights with the weights 11, 12, 1, 2, 1, 1, 1, 2, 1, 3. So if you go back,
let me go back. Is he talking about this?
Yes, that one.
Both are columns. Yeah, this is a column, this is a column. This is a matrix, actually. What exactly Akash wants to know? Yeah, Akash, you can talk. Helena, can you unmute him?
Hi, Pranjal.
Yeah, hi, Akash.
Yeah, I mean, when you were explaining, you said with whatever weights are going from the first input layer to the hidden layers, it will be as a row, and then the other one would be as a column. But it is looking like it is actually the first. To the first hidden layers, it is the first column, and the second hidden layers is the second column. If there's a third one, it would be a third column. There is nothing like a row in this. I just wanted to confirm whatever I'm saying is right.
Okay, let's look at this weight matrix. Okay, and this weight matrix, you have the number of nodes over here. Okay, which this is going from W1n all the way to Wn. So basically, this is okay. Maybe I should have put it a little. I could have put it a little differently. Yeah, I think that's where the confusion is. So I said like the weights leaving the nodes. Instead of saying the weights leaving the nodes it's basically the number of nodes that you have from where the weights are originating. So the number of nodes from where the weights are originating. So you have x1 all the way to xn. Okay. So this is how your weight matrix is aligned. The number of rows is having the number of nodes from where the weights are originating. Okay. And the number of columns is equal to the number of nodes that you have in the output layer. In this case, for the sake of simplicity, our output layer is this. And you have H1, H2, and H3. So this is for H1, this is for H2, and this is for H3. You think this is clear to you now? Is he saying?
Yes, it's understandable now. So
okay.
he's
yeah. So I think that's where I put it a little incorrectly. I'll make that change in the presentation. Yeah. Thanks for pointing that out. Okay. How do I move forward? Whenever I click chat, it becomes difficult to move forward. Okay. Okay, so now we have exactly 15 minutes. Shall I move forward with this because we still have almost 20 slides?
Yes, we have another approximately 15 to 20 minutes, so it depends.
Okay, so let's see if I am able to give an intuition about backpropagation. I think that would be it for this session, because getting deep into the maths of backpropagation, I don't think we have time. And I also ran out of time while creating PPT, okay? So, okay, we know how to calculate the output of a deep neural network, okay? You put in some inputs, you threw in some inputs, you got some output. You put in X bar, you got Y bar. Now, what if you get the wrong output? Okay, so to figure out what if you get the wrong output and how do you correct that output, first you need to define how wrong the output is. Okay, you need to be asking the right questions first before you give the right answer. So the right question is how wrong the output is. And how do you define how wrong an output is? You basically define an error. So in our case, an error could be you want to predict, you input a cat and then, and the output in your network is calculating a fish. However, your output should have been a cat. So your output, so the error becomes desired output minus calculated output. Okay. So it's not exactly cat minus fish, but it is desired output minus calculated output. So more formally, you define error as D bar, which is your desired output vector. Error is your E bar, and desired output vector minus Y bar, which is your output vector. Okay, which is your calculated output. So desired output minus calculated output. And we also call this as, we can also square this and call it as loss function. Why we square this? Because when we square this, everything is just positive. Okay, so be positive, make sure your error is squared. Okay, and we also sometimes divide it by 2 because it just makes the backpropagation calculation a little easier. So it's totally how you want to define it. So let's see what we want to do now. Okay, a mathematical approach to error. What we want to do now is we want to adjust the weights so that our error is minimized. That is what we want to do. We have weights W1, we have weights W2. We want to find the best weights so that our output Y bar is as close as possible to Y. That is what we want to do. To figure out the weights, what we need to do is we wish to find how Y or error is changing with respect to the weights. Okay, mark my words, with respect to the weights. How the error is changing with respect to the weights. Whenever I say with respect to the weights, some variable changing with respect to the weights. If a function fy is changing with respect to the weights with respect to x, you know what is coming. Drum rolls, partial differential calculus incoming, and you know this person very well. Okay, so first, before we get into that, we need to understand what is gradient descent. So assume we have only one neuron. Okay, assume you have just one neuron, and you have, of course, just one weight. So the way the whole maths is rigged around perceptrons and deep learning neural networks, usually our error is a convex function. Okay, this is a convex function, and I think it's convex. Yeah, I think that's convex function. So usually your error is defined as a convex function, and the way your error changes with respect to your weight is something like this. It's usually not this nice unique U shape, but it's more jagged, but that's how it is. So let's say you predict some output y cap, and you calculate the error, and your error is over here. Okay, so what you want to do, if you want to minimize the error, you increase the weight like this. You increase the weight slightly, so then you like, you know, your error comes somewhere over here. Then in next iteration, your error is even lesser till you find a, till you reach a very, you know, low point in the error, or your desired accuracy, whatever comes first. So if you have 3 neurons and 3 weights, no, it is not as beautiful a picture, but more or less that's how it's a way to visualize things. You can have different weights. For different set of weights, you know, the error can be at different parts. So what you want to find is the best combination. And the algorithm to find this best combination is known as gradient descent. Gradient descent, okay? This is how usually error looks like. This is actually a oversimplification, but you know, that's how mostly it is. So there are some local values, but you ideally would want to reach the absolutely the lowest one. Okay. Excuse me. So more precisely, what you want to do is, let's look at this one. So if you are at this point B, okay, and you want to decrease the error, what you calculate is you calculate the slope of this. You calculate the slope of this this function at this point. When I say slope, it can be also termed as gradient. Okay, this is the gradient that we are calculating. So if you see the gradient is over here, the slope is, you know, slope is going up. It's moving upward. You see the slope is moving upward. What you do is you decrease the weight. If you decrease the weight, you know, in this direction, the error is going to go down. Similarly, on the other side, on the left hand side, you see you want to decrease the error. You calculate the gradient. You see the gradient is negative. What you want to do is you want to increase the weight. So remember, gradient is positive, you want to decrease the weight. Gradient is negative, you want to increase the weight. There is an inverse relationship, okay? There is like negative of the gradient. And that's exactly what we are going to do. So there is an inverse relation between weights and the gradient, okay? So if alpha is your learning rate, and you want to find, and you find this, the value to this expression, which is del E by del W, which is rate of change of error with respect to weights, then your new weight is going to be whatever was the previous weight plus alpha multiplied by negative of this partial derivative. By the way, this, you know, this equation, go back to the initial slides. I'll share the presentation with them. If you remember the initial slides, okay, there was we were in the perceptron algorithm, we were making this change W plus alpha W, okay? That is exactly what is happening over here, except that, you know, you have a whole matrix of weights and everything is just way more complicated. And this is exactly what is happening. So alpha is your learning rate, and partial derivative. Why we take partial derivative? Why don't we just take the derivative dE by dW? We don't take dE by dW because there's not just one dW, guys. There's just so many weights, and you want to see how error is changing with respect to each of those weights. Okay, how error is impacted by each weight separately. Okay, so that's why you take del E by del W. And this is a vectorized format of this equation. This inverted triangle is basically your gradient. So the gradient of weights minus E, so because they are invertly related. That's what you're going to do. So now let's develop, okay, we have 5-6 minutes. Okay, so let's develop some intuition for backpropagation. I think we should be able to finish in time. Generically speaking, if you have a layer K, these are your hidden layers. This is your input. This is your output layer. This is your input layer, and you have these K number of hidden layers. So from hidden layer K to K plus 1, if you want to update the weight, Wij. So Wi, this is like leaving from node I and going to node J in layer K plus 1. How are you going to update the weight? This delta W K, just ignore this Kij. Just try to understand how you're going to update this weight between these two layers. Okay. So the way to update these layers is you calculate how error is changing with respect to this weight, and then you just calculate this delta W, and you update your weight new like this, W previous plus delta W. Okay, these subscripts and superscripts just make everything look a lot more complex. But what we are doing is exactly this. We are just changing our weights by measuring how much the error is impacted by that particular weight. That particular weight is important. So this is exactly what we are doing, and this is what backpropagation is. This is the intuition to backpropagation. You're going back from, you're basically updating weights and figuring out how much that weight is affecting the error. And if it is affecting the error more, you basically change it more than the rest of the weights. Okay. So you need to understand, you do not get an exact number. Okay. The calculation is not going to give you, okay, you just increase weight by 5 and you will be good. No. Calculation is going to tell you only this: increase the weight more or less, and relatively more or less than the other weights. That's what you're going to do. That's what you're going to get from backpropagation. So this is a good example of backpropagation. It was there in, I think, one of the notebooks. So you want to figure out how much W1 is affecting your output Y. Okay, L is your loss. So you apply chain rule. Okay, backpropagation is nothing but gradient descent coupled with chain rule. Okay, so you see how loss or error, you can call this error because we have been calling this error so far. So how error is changing with respect to output L2. This is the hidden layer. Okay, then we see how this, then we apply chain rule basically. Then we move to this node. We see how loss is changing with respect to S. To calculate how loss is changing with respect to S, you calculate how loss L2, how L2 is changing with respect to capital S, multiplied by how loss is changing with respect to L2. Similarly, you go down another step, you calculate how loss is changing with respect to L1, which is nothing but how S is changing with respect to L1 and loss is changing with respect to S. So you basically, you use this, product, and you basically fit over here. So it becomes a big equation. And then you drill down right down to the last weight, and you do how the loss is changing with respect to weight 1. Okay, this is del W1. High enough. Okay, so this is what you're actually calculating, how your loss is changing with respect to W1. And you apply basically chain rule, del L1 by del W1. We calculated del L by del L1. You basically substitute this. Then when you have over here, you have S del S by del L1. For del S by del L1, you actually substitute this. Sorry, for del L by del S, you substitute this. You keep on substituting. This becomes a very long, multiplication of weights, and you'll get to know how much the loss is affected by weight 1, W1. Okay. So I will end with this interesting conversation we had in the Slack group, where somebody asked, what is the difference between gradient descent and backpropagation? So think about it like this: gradient descent is a CEO of a company. Okay, he's trying to minimize the losses of the company. Okay, he just cares about minimizing the losses of the company as a whole. And of course, he's giving a hard time. He's pulling all the strings and giving a hard time to the managers. And backpropagation is that team of managers which goes on around, moving around and putting the blame on the employees. Your employees are nothing but your weights, W1, W2, W3, W9. Okay, so sorry, I ran out of time. I was fairly accurate that this will run for 1 hour and 15 minutes. So that is it.